Hello, my name is Tulio Machado, and I'll be presenting design of compressed variable stiffness panels with steering thickness coupling, a work developed in cooperation with Professor Hernandes, Victor Capacia, and Saulo Castro. This work focuses on a mass optimization of a wing upper skin stiffened panel. Only a single wing bay of the wing upper skin is considered, as you can see, at the wing root. This panel is under compression, so the optimization considers linear buckling as the failure criteria. Variable stiffness laminates are applied in the panel skin, subjected to manufacturing constraints and coupling between fiber steering and laminate thickness. The optimization is carried out using a genetic algorithm which is integrated to MSC Nastran solver. Symmetry boundary conditions reduce the amount of design variables needed and computational costs for finite element analysis. The figure on the left shows our entire wing bay configuration. The region highlighted in red shows the unit cell representative section, from where our finite element mesh is defined, as shown in the figure on the right side. Constant quad elements are used in the entire model, and compression is applied by a nodal force which is distributed to the nodes at the front edge by means of a rigid element. Physically, this formulation implies in a modular design, where the unit cell configuration is repeated over the width of the full panel. So why do we use variable stiffness laminates in the design? Automated manufacturing techniques such as automated fiber placement and constant toe shearing can produce curvilinear fibers. This extends design possibilities as spatially variable stiffness enhances structural tailoring when compared to traditional laminates. Also, previous works have shown potential improvements in buckling loads for plates, cylinders, and stiffened panels. In this work, we will consider both manufacturing processes to observe their impact in the optimization. For AFP, we have a constraining steering radius of 500 millimeters, and for CTS, the constraining radius is 50 millimeters. Steering to thickness coupling happens in both processes. AFP can either produce local thickening regions due to the formation of overlaps or constant thickness using the cut restart technique. For the latter, we have a drawback of increased manufacturing time. For CTS, the only option is a continuous thickness distribution related to the in-plane shearing. To define a curvilinear path that varies along the y-axis, we must specify the reference angles at the control points. Let us consider that control points are located at the edges of the unit cell, so the angles at the edges of the unit cell are represented here by T11, and they are located also in the middle section of the unit cell. The angle is represented by T12. This formulation guarantees fiber continuity from one unit section to the other. Once the angle at the control points are known, by using a Lagrangian interpolation, we can define all fiber orientations in the finite element mesh based on each element position. Steering to thickness coupling is performed in this step, as each element is assigned with a specific property whose thickness is a function of the steering angle. By knowing the fiber path, we can evaluate the steering radius distribution over the laminate plane by using the radius equation in a Cartesian coordinate system. The minimum steering radius within each ply must be higher than the constraining steering radius from the chosen manufacturing process. Optimization design variables are related to geometry and layup of the unit cell representative section. Regarding the geometry, we have the unit cell width, represented by letter B, the stringer height, and the stringer foot width. In this work, the unit cell width corresponds to fractions of a 840 mm wide stiffened panel. Thus, the product of the number of stiffeners and the unit cell width is constant. By knowing the design variable B, we know the number of stiffeners in the full wing bay panel. The stringer layup is composed of balanced and symmetric constant stiffness laminates using conventional fiber orientations. For the skin layup, only variable stiffness laminate layers are used. We only assume the layers are balanced to each other. To calculate the load acting on the unit cell finite element model, we use the same design bending moment at the wing root to all individuals in the optimization. As we know all design variables from one individual, we can define for that individual a specific geometry of a wing box configuration. Then we can determine compression stresses based on design bending moment at the wing upper skin using a structural idealization of the wing box section. This provides a rapid tool to determine compression stresses. The characteristics of each individual will affect how stresses are distributed over the idealized section. From that, we can determine the load acting on the finite element model and run the buckling analysis. Here's the complete structure of the genetic algorithm developed in this work, considering classic genetic operators. So far, we cover how the Nastran bulk data files are assembled. Next, we'll go through the fitness evaluation and a brief explanation on the design constraints. The optimization consists on minimizing the mass of a single wing bay. The fitness value is based on the mass of the unit cell, the number of stiffeners in the entire panel, and the product of penalty functions for design constraints, which are buckling load, ply proportions, ply contiguity, and steering radius. This chart shows how the penalty function behaves as each constraint is violated or not. In the third column, you can see the values assumed by each penalty function associated with each constraint. 4 optimization cases were performed in this study. A baseline design using constant stiffness laminates in both skin and stringer was performed to serve as a basis of comparison. Then 2 cases using AFP, one with constant and the other with variable thickness, and 1 case using the CTS process. The optimized parameters are summarized in this chart. As you can see, the minimum steering radius was achieved in all optimizations, and the mass reduction ranged from 13 to 15% in comparison to the baseline. Also, our optimal designs contain 7 to 8 stringers in the full panel, with 8 being the maximum allowed in our optimization. This shows us that more subdivisions lead us to lighter solutions. Here are the optimized stacking sequence for all cases, and we'll focus on the results for AFP with variable thickness and CTS. Here is an exploded view of the optimized AFP skin layup. Only one ply of every balanced pair is shown for simplicity. Note that darker regions shows the AFP local thickening due to the overlaps. Angle variations between control points at the edges and at the middle section of the unit cell are relatively small due to the AFP constraining steering radius of 500 mm. Small variations between the membrane stiffness is shown in the polar plots in the figure on the left. The resultant skin is a soft laminate, and the stringer provides much of the axial loading carrying capacity of the panel. In a similar way, we have the results for the CTS panel. Continuous thickening due to shearing is represented by darker shades in the plot. The polar plot at the control point in the center indicates that layers are more aligned with the load in that region where the stiffener is located. Note how the membrane stiffness changes rapidly from the control point at the edges to the control point at the middle section of the unit cell. Such tailoring potential is due to the smaller constraining steering radius of the CTS process. As we can see, we had an overall mass reduction ranging from 13 to 15% in comparison to the baseline. Also, we could observe the effect of the constraining steering radius in optimal design based on different manufacturing processes. Finally, the optimal design resulted in more stiffeners within a wing bay. Suggestions for future works include relaxing the balanced laminate hypothesis adopted in this work. Instead of using a modular design, optimizing the entire panel, as well as more wing bays along the wingspan. Also, the entire wing box can be optimized using more complex loading conditions, considering the bending twisting coupling of the wing. I would like to thank you all for your attention, and I hope you have enjoyed this presentation. If you have any questions, I'll be pleased to answer. Thank you.